So the next talk will be given by Roman Krems from the University of British Columbia on the fully uncoupled space-fixed coordinate basis representation for molecular collisions in the presence of external fields and the spherical tensor formalism for atomic and molecular interactions.
Well, thank you very much, and it's a great pleasure for me to speak. It's a particular honor for me to speak here today. Like Ruben, I never played squash or tennis with Alex because by the time when I came to ITAMP in 2001, Alex's fame as squash player was so great that I was intimidated to ever play with him. In retrospect, I think I should have, just to have something to say about this. But and I apologize for the length of my talk title in the book of Astrophysics. I thought very hard about how to make it stand out, and I couldn't think of anything better than making it long. In any case, currently I'm at the University of British Columbia, and this is a picture of our campus. I both live and work on campus. And every day, when I look at the mountains, as much as I liked Boston, I feel very happy there too. So what I really am going to talk about today is theory of atomic and molecular collisions in the presence of external fields. And the outline of my talk, here's the outline of my talk. In the first part of my talk, I'm going to briefly describe two papers Alex and I wrote. Well, we wrote more than two papers, but two papers that I think are most significant of the papers Alex and I wrote when I was working with him in the period of 2001 through 2005. I came to work with Alex as an SAO predoctoral fellow in 2001, and then I stayed as a postdoc. My postdoctoral position was funded by the Center for Ultra-Cold Atoms, so my affiliation on my CV changed, but I actually stayed in the same office and enjoyed the collaboration with Alex throughout my tenure as postdoctoral fellow here. So what I'm going to tell you about today is the work, the two papers I did with Alex in 2004 actually. And the reason I wanted to tell you about this work is because this work has been instrumental in the research I pursued ever since. As I was building my group at UBC in 2005 through 2007, one of my group's former members, Timur Cherbil, is now working with Alex. And so Alex and Timur are continuing some of this work, and of course we're also continuing some of this work at UBC. So in a sense, we're working with Alex again, but now in parallel. Okay. So before I tell you about how we do the calculations and describe the specific results, I wanted to spend a couple of minutes and tell you why why we were interested in collisions in external electric and magnetic fields. And when I first came to ITAMP in 2001, that was the time when people like John Doyle were actively thinking about cooling and trapping molecules. And as you know, a lot has been already said at this conference about cooling molecules into ultra-cold temperatures, about the creation of ultra-cold molecules. And as you know, molecules are cooled to cold and ultra-cold temperatures by evaporative or sympathetic cooling in external field traps. Basically, what you can find a molecular sample, it's an atomic or molecular sample, in an external field trap, and then you cool this sample by evaporative or sympathetic cooling. And the cooling relies on elastic collisions within the sample. Now, if you prepare your molecules in a metastable excited state, such molecules will then may then collide elastically as well as inelastically. Now, the elastic collisions are going to be important for cooling because they lead to energy rethermalization in your cold sample. And and the inelastic collisions are going to remove molecules from the trapped gas. It happens in the region where the density of the gas is the largest, which is near the center of the trap. That's where the molecules are the coldest. Therefore, inelastic collisions will remove some of the coldest molecules from the sample and lead to heating of the trap. Therefore, in order to understand the prospects for cooling specific molecules, atoms or molecules to ultra-cold temperatures, it's critically important to understand the efficiency of elastic scattering and the mechanisms of inelastic scattering of these molecules, atoms or molecules, in the presence of external trapping fields at cold and ultra-cold temperatures. So before 2001, there was really no theory to do rigorous quantum calculations for molecular collisions in the presence of fields, and that's what we set to develop, when I started to work with Alex. Now, external fields modify. I don't know what that is. Oh, is this just my mouse? So external fields may also modify binary interactions between atoms and molecules in a cold gas, and that may be used, to control intermolecular interactions, and that might ultimately lead to controlled chemistry. As we know, from the work with ultra-cold atomic gases, external field control of binary interactions between atoms, is used to control macroscopic properties of ultra-cold matter. So if we know how to control interactions between molecules, we may then have similar tools to control macroscopic properties of ultra-cold molecular gases. Finally, interactions of molecules with fields may be used to create or to study new regimes of molecular dynamics. For example, you can use laser fields are used to confine or generate ultra-cold atomic gases in low dimensions. So if you do the same with molecules, you may be able to study molecular dynamics in restricted geometries, which may be very interesting. Misha Lukin told us yesterday about how confining molecules on optical lattices may lead to a lot of interesting applications in several different subfields of physics, such as condensed matter physics and quantum information science. So by generating optical lattices of molecules, you're kind of opening a new chapter in the research of ultra-cold molecules and several related fields of physics. So interactions between molecules and fields are very important for research of cold molecules, and that's what Alex realized, even before I came to ITAMP, and that's what we began to work on when I came to work with him in 2001. Now, before I tell you about how we do the calculations of molecular scattering in the presence of fields, I wanted to review the very basic principles of collision theory. So whenever two particles A and B collide, so to describe scattering of two particles A and B, we normally solve the Schrödinger equation with the Hamiltonian that generally looks like this, where we have HA, H sub A, and H sub B describing the separated particles A and B, and V is the interaction term, including, of course, the kinetic energy for the relative motion of the colliding particles. So the standard approach to solve the Schrödinger equation is based on the so-called close coupling expansion, where you expand the total wave function, the eigenfunction of the total Hamiltonian, in terms of the eigenfunctions of the Hamiltonians H sub A and H sub B, like this. And it's the easiest approach is based on calculating these eigenfunctions of H sub A and H sub B in the so-called molecule fixed coordinate frame. That is the coordinate frame associated with the collision complex, where the quantization axis is determined by the collision complex. And it's the reason people do it this way, and most of the time, is because this simplifies the evaluation of the matrix elements of the total Hamiltonian, in particular the interaction potential between the colliding particles, because the interaction potential between the colliding particles is normally calculated in the molecule fixed coordinate frame. Now, the other thing that people used to do, most often do for scattering calculations, is they couple all the angular momenta. Like the colliding particles A and B may contain internal angular momenta. They may contain spin angular momenta. They may be described by rotational angular momenta. So most of the people, when they do scattering calculations, they couple all of the angular momenta to basically rewrite this closed coupling expansion in terms of eigenfunctions of the total angular momentum of the system. And this is what Alex and his colleague did in this 1960 paper. And since 1960, this is what this is referred to as the Arthur-Dalgarno representation. So the advantage of the Arthur-Dalgarno representation is that the Hamiltonian matrix, in this representation is block diagonal. It looks like this, where the different blocks correspond to different total angular momenta. So the scattering problem can be solved for different total angular momenta separately, and this, of course, simplifies the problem significantly. Basically, you're breaking the big problem into a subset of smaller problems. Now, if you apply an external electric or magnetic field, the total angular momentum of the system is no longer conserved. Mathematically, what that means is that the interaction with external fields is going to induce couplings between blocks of the different total angular momenta. So your Hamiltonian will now look like this, where the off-diagonal matrix elements are induced by the molecule or atom field interactions. So the first thing we realized when we started to think about the scattering theory of collisions in fields was that the Arthur-Dalgarno representation is no longer going to be useful for our purposes. Sorry about that, Alex. And the other thing that we had to do was to the other thing that we realized is that the molecule fixed representation for the basis functions again would not be good, because in the presence of fields, the external field defines a specific laboratory fixed quantization axis. So we had to reformulate the whole collision problem without the Arthur-Dalgarno representation and using the space fixed coordinate frame. So basically now the functions, the eigenfunctions of the Hamiltonians H sub A and H sub B had to be calculated directly in the lab frame, defined by the direction of the external field axis. And in the way we chose to formulate the collision problem, we chose to do it using what we call the fully uncoupled representation. And I'm going to clarify what I mean by this by this simple example of a collision between two doublet sigma molecules. So a doublet sigma diatomic molecule is characterized by rotational angular momentum, and also it has a one unpaired electron. So it will have a non-zero electron spin. So if we were to do a scattering calculation for collisions between two doublet sigma molecules in the presence of a magnetic field, we would use the basis set like this. The basis set of direct products, where we would have the rotational wave function of molecule A, the spin wave function of molecule A, the rotational wave function of molecule B, the spin wave function of molecule B, and the rotational wave function describing the rotation of the two molecule collision complex, the end over end rotation, in the space fixed coordinate frame. So all of these functions, all of these wave functions, are going now to be calculated and defined in the laboratory fixed frame. So all of these projections here are projections with respect to the magnetic field axis. And that is important So this, so we use this, representation to reformulate the collision theory, and all of the calculations we nowadays do are carried out in this kind of the representation. The problem, or the first difficulty you would encounter if you wanted to do a scattering calculation in this representation would be the evaluation of the matrix element of the interaction potential in this basis set, because as I've already told you, the interaction potential between colliding particles, between atoms and molecules, is normally calculated, in the molecule fixed coordinate frame. This is the natural frame. This is the natural coordinate system for the interaction, for the interaction potential, for the electronic interaction potential between atoms and molecules. So in order to evaluate the matrix elements of the Hamiltonian, and in particular the interaction potential between the colliding particles, the first thing we have to do is to reformulate, basically to rewrite the interaction potential directly in the space-fixed coordinate frame. Because now what our basis functions are defined in the lab frame, in the frame determined by the direction of the external field axis. So we have to rewrite the operator for the electronic interaction potential in the same frame in order to evaluate the matrix elements of the Hamiltonian in a consistent way. And for two molecules, it's actually quite easy to do. For two closed shell molecules, for two molecules without unpaired electrons, it's easy to do because we can, and this has been done before us, of course. So for two molecules, we can write, whenever we have, the electronic interaction potential between two molecules is a function of these three vectors. RA, the vector that specifies the orientation of molecule A, RB, the vector that specifies the orientation of molecule B, and the vector R, capital R, that specifies the orientation of the intermolecular axis. And with a little bit of angular momentum algebra, it's easy to show that any function of these three vectors can be written like this, where we have a product of three spherical harmonics, each depending on one of these three vectors separately. So we have one spherical harmonic depending on the orientation of the vector RA, another one depending only on the orientation of the vector RB, and the third one depending on the orientation of the vector capital R. Now, if we have this representation of the interaction potential, it becomes straightforward to evaluate the matrix elements of the interaction potential in the basis I showed you on the previous slide, because these spherical harmonics, they can be defined in any coordinate system, including the lab frame, right? So these projections here, the m sub lambdas, they can be projections with respect to the external field axis. Now, a more difficult problem is to write the electronic interaction potential between two molecules or two atoms containing unpaired electrons, two open shell atoms or two open shell molecules. Because in this case, like in the case of two closed shell molecules, we have very well defined vectors RA and RB. In the case of atoms, we have unpaired electrons, and we can't specify a vector like this that would describe the rotation of electrons inside the atom or the molecule. However, back in 2004, also with the help of Harvard-Smithsonian, we showed that the interaction potential between atoms in arbitrary electronic states can be written in a rather similar form. Now, it's not exactly the same form. You may notice that I have T's here. These are spherical tensors. I'm not going to go into details about what the spherical tensors are. Bernard Ziegelman told us a little bit about this yesterday. But this is not the point I'm going to try to make here. So the point I'm trying to make here is that this expansion here is very similar to this one. I mean, these tensors are slightly different from the spherical harmonics here. But the bottom line is that these tensors can be defined in the space fixed coordinate frame. Basically, they can be defined in any coordinate frame. So I can write any electronic interaction potential, any electronic interaction potential between any two particles, between any two atoms in any electronic states in a form like this, where again I have a direct product of spherical tensors each defined in any coordinate frame. With this, I have all the formalism to evaluate the matrix elements of the electronic interaction potential in the uncoupled space-fixed basis set I introduced a couple of slides ago. So these are the two papers. We published them in 2004, and I think these two papers are. I think of these two papers as most significant of the papers Alex and I wrote when I was here, because they kind of set the ground for the machinery for the scattering calculations we did thereafter. And what I'm going to do in the remaining part of my talk, I'm going to show you a few examples of how we used this formalism to solve or answer specific questions of interest to experimentalists in the field of cold atoms and molecules. Now, the first example I was going to talk about is this calculation of collision properties involving non-S-state transition metal atoms. We did this back in 2004, 2005, and prior to 2004, all of the atoms that were confined in magnetic traps and cooled to ultra-cold temperatures were in the electronic S state, like alkali metal atoms or metastable helium. So the question we had on the table then was whether other atoms, because the periodic table is much more than just S-state alkali metal atoms. You know, there's a lot of this actually the majority of atoms in the periodic table are non-S-state atoms. So the question we asked back then was whether cooling of non-S-state atoms is going to be possible, or is going to be as easy as cooling S-state atoms in magnetic traps. And the spherical tensor formalism and the uncoupled representation that we developed allowed us to do rigorous scattering calculations for collisions involving transition metal atoms. In particular, we did our calculations for these two transition metal atoms, scandium and titanium. And the electronic configuration of transition metal atoms is such that in addition to the non-S-state unpaired electrons in the 3D shell, there are these 4s2 paired spherically symmetric electrons. And now the particular question we were trying to answer with this calculation was whether the presence of these outer shell spherically symmetric electrons would somehow have an effect on collision properties of of transition metal atoms. And the calculation showed that indeed the transition metal atoms, due to the presence of the spherically symmetric 4s2 electrons, transition metal atoms behave upon collisions effectively like S-state atoms. In the language of Bernard's talk yesterday, this means that the electronic interaction and anisotropy between transition metal atoms is suppressed. So John Doyle then carried out an experiment in which he measured basically the same properties as we calculated in this work, and so our results agreed. And he also went on and did the experiment with rare earth atoms, and this led to this Nature paper where they reported the magnetic trapping and cooling of rare earth atoms. Now, the fully uncoupled space-fixed representation allowed us to develop the scattering theory of molecules in the presence of combined electric and magnetic fields. And this was the first paper Timur and I wrote on this in 2006. Now, so this is the system we studied in this paper was the collision system involving doublet sigma diatomic molecules for a number of reasons I'm not going to go into. But this is a diagram, a schematic energy diagram of a doublet sigma diatomic molecule in a magnetic field. basically the rotational energy levels of a doublet sigma diatomic molecule are characterized by the total angular momentum J, which is the vector sum of the rotational angular momentum and the electron spin of the molecule. So the ground rotational state of the molecule J equals 1/2 splits in a magnetic field into two Zeeman sublevels, and it's this spin up state that is trappable in a magnetic trap of John Dawes experiments. So back in 2003, Alex and I showed that upon collisions, the spin relaxation, basically the relaxation from the spin up state to the spin down state in doublet sigma molecules occurs through by a mechanism involving coupling to the rotational excited state. Basically, to go from this state to this state, you have to couple to the rotational excited state, and the spin-rotation interaction in the rotational excited state is going to convert, basically, to flip the orientation of your spin, resulting to the transition to the spin down state in the rotational ground state. Imagine now what happens if we apply a strong magnetic field. The energy level of this spin up state is going to go up, is going to increase. The energy level of this rotational excited state is going to go down, and at a certain magnetic field, these energy levels are going to cross. So, and this is what this crossing is, where this crossing is for the particular example of a calcium H molecule. If you now apply an electric field on top of the magnetic field, this crossing, which is a true crossing, will become an avoided crossing. In the absence of electric fields, like I said, this is a true crossing because these states are of different symmetry. Now, an electric field converts this crossing into an avoided crossing, and as a result of this, the electric field has a dramatic effect on the spin-changing transitions in collisions of such molecules. And this is illustrated by this graph here. So, if you look at the black curve here, the black curve is the cross-section, or the probability for the spin-up to spin-down transition in collisions of calcium H. And this particular calculation is for collisions of calcium H molecules with helium. So the black curve is the probability for the spin-up to spin-down transition in collisions of calcium H molecules with helium in the absence of electric fields. As you can see, the magnetic field here is varied. To go through this crossing. So as you can see, this crossing has no effect on the spin-up to spin-down transition in the absence of electric fields. However, if we apply an electric field of as little as 20 kilovolts per centimeter, the picture is going to change dramatically. Like this red curve corresponds to is from the calculation with an electric field of 20 kilovolts per centimeter. And as you can see, there is a huge, humongous peak in the probability for the spin-up to spin-down transition that occurs right at the position of this avoided crossing. Now, here is a three-dimensional plot of the probability for the spin-up to spin-down transition as a function of magnetic and electric fields. And as you can see, at certain combinations of electric and magnetic fields, this probability is dramatically enhanced. Now, why do we want to manipulate this kind of a process? Well, one application could be the study of controlled chemical reactions in a magnetic trap. Imagine you have a chemical reaction between a doublet S atom like sodium and a doublet sigma diatomic molecule like calcium H in a magnetic trap. If you trap both atoms and molecules in a magnetic trap, their spin angular momenta are going to be aligned like this. So when trapped atoms and molecules, when trapped doublet S atoms and doublet sigma molecules collide in a magnetic trap, they're going to interact via the triplet state, via the state with the total spin S equal to 1. And the chemical reactions of atoms with molecules on triplet states are normally suppressed because they have significant reaction barriers, like schematically shown in this diagram here. If you, however, flip the orientation of either the spin of the molecule or the spin of the atom and the molecule are going to interact on the singlet state potential surface. In chemical reactions of atoms and molecules on singlet states are usually much faster, because a lot of times they occur without chemical reaction barriers. They are of insertion type. As I just showed you on the previous slide, by applying combined electric and magnetic fields, we basically have a tool to flip the orientation of the molecular spin in collision processes. So this could be used to effectively transfer molecules or the collision complex from the triplet state potential surface to the singlet state potential surface in the course of a chemical reaction, and thereby control the efficiency of a chemical reaction in a magnetic trap. Now, the last 2 minutes, if Françoise allows me, in the last 2 minutes I wanted to draw your attention to this paper that Timo wrote just a few months ago. This was a major work in which he basically combined the theory that Alex and I developed with his expertise in reactive scattering calculations to produce a theory of chemical reactions in the presence of electromagnetic fields. As a result of this work, we developed a scattering code which can be applied to study effects of electric and magnetic fields on chemical reactions of atoms and molecules. And we did, in the first paper reporting our results, we did the calculations for the lithium plus HF chemical reaction. And this is my last slide, where I just wanted to show you that at temperatures on the order of 1 Kelvin or below, the probabilities of chemical reactions are very sensitive to external electric and magnetic fields. Now, this calculation was for the lithium plus HF chemical reaction in the presence of electric fields. And as you can see here, the electric field may modify the reaction rate by several orders of magnitude. Now, this is the bottom line of my talk. What I tried to communicate to you today was that the fully uncoupled, the combination of the fully uncoupled space-fixed representation, the formulation of the scattering theory, and the fully uncoupled space-fixed representation with the spherical tensor formalism for the electronic interaction potentials between open shell atomic and molecular species, is a powerful method that allows us to study, a variety of different applications, for dynamics of low-temperature gases. I want to finish with a slide of references that I didn't have time to talk about. One particular paper I wanted to draw your attention to is this one that we wrote with Harry Tronenboom and Shi Chu. This was the continuation of the 2004 paper applied to long-range interactions now. This paper, if you're interested in cold chemistry, this paper summarizes some of my most recent ideas on what all of this can be interesting for. And thank you for your attention.
The paper is now open for discussion. Yes? Please take the mic.
The question was, is this the work that we needed a 15J symbol for? The answer is no. This is the work we needed an 18J symbol for. So basically, the expansion coefficients in the formula I showed you, they can be related to the Born-Oppenheimer potentials of the diatomic molecule, and this relation can be written in a very compact form using an 18J symbol. When I showed this work to Chris Green, he told me that once he had to work with a 52J symbol.
Franco?
Roman, one of the reasons why people have abandoned the uncoupled representations many years ago was because of the fact that you had this proliferation of angular momenta, and therefore you don't have the block diagonalization that you showed as being very useful. Now, once you lose this advantage, as you have actually very clearly shown, then the problem becomes again very complicated. And where do you can cut corners on the computational levels? One advantage is the fact that you're moving down in energy. So the number of angular momenta that are coupled, at least translationally speaking, will be much fewer. You're essentially doing S-wave scattering. But there anything else where you can actually simplify the picture of the coupled channels?
Yeah, that's a very good question that I've been thinking about for quite some time now. And if you look at this matrix that I showed you early in my talk, one thing that you may notice, if you analyze the structure of this matrix, is that the field-induced couplings, they only couple, the adjacent J's, right? What's that? Right, it's tridiagonal structure of the matrix, and I'm sure there, one could come up with a procedure where you would somehow iteratively calculate the whole scattering problem, do this whole scattering problem by basically breaking it down into a smaller subset of problems. I've never managed to come up with a sensible procedure to do it, but I'm sure, this can somehow be used. And I told my students to try and explore this, but none of them seem to be were interested as of yet. So no, as of today, we don't know how to simplify this yet, but I'm sure there should be a method. There is a procedure one can come up with. And now that I know that you're interested in this, maybe your students could try and come up with it. I'd be happy to share my ideas with you more.
Thank you.